Yeah, another video. This one responding to Hythloday, who has announced himself as a supporter of the light carries momentum theory. Now, I've seen quotes of Einstein, where they basically just say Einstein said you can't make light go faster. But I don't know. Maybe there's no specific quote about light carrying momentum, but yeah, it can't carry momentum. But anyway. Alright, so we're back to this spaceship analogy, and so you have a spaceship moving, just a hollow one, doesn't have to be very interesting at all, and it's moving half the speed of light that away, and you shine a beam of light across, and you mark perpendicular, and the theory is what they're saying will happen is the light will go straight across the ship and hit the perpendicular, even though the perpendicular is moving in this 4-foot distance. Let's say the spaceship will move 2 feet. So this dot will move 2 feet in the same amount of time it takes for this light to get here, and yet somehow, by some miracle, the light will have figured out how to go this way. Now, the obvious math is obvious, but let's just draw it real quick. Okay, I should do more precise lines, but the hell with it. The idea is these would be the two momentums, right? And so you have the speed of light, and that gives you a certain point, and that's this point here. And so if I give this thing velocity, what I'm essentially doing is creating a diagonal. So then all I have to do to break the speed of light, that is travel more distance, see, this line is shorter than this line. So the faster I go this way, up to the speed of light, the same length, let's say about there, the more I have essentially violated the speed of light. So the idea is if I take a flashlight and just move my arm this way, I will have actually made the light arrive at that diagonal point, faster than the speed of light. So all I have to do is ride on a train and shine a light off the train, and the light will jump into the future to hit the target, okay, that is coming towards me. So there's a sign coming towards me. I'm on a train. Yeah, I just shoot the light sideways. I don't have to shoot it at the sign. I just shoot it sideways and it'll go to the sign. Like a baseball. It'll have my momentum. So light can go 2 ways at once. I guess it could go 3 ways. So I could add a third vector. So yes, let's add the y-axis, the z-axis, right? So if we z this thing and I give it 2 extra momentums, then I can get even more extra speed of light out of it. So it seems to me this is probably how you can make one of those subspace communicators. Is you just make a few of these boxes. You just take like some sort of radioactive isotope and you shoot it, at 90% of the speed of light. And you know that in exactly some other seconds it will decay and produce a photon. And then you just receive the photon on the perpendicular, and you will have traveled the extra distance of the diagonal. So there you go. We can time travel all we want now. So thank you, Hythloday, for helping me build. I'll build a time machine now, right? Because gee, I didn't know it was possible. Now, hey, it is possible. I can make light go faster. So yeah, Nobel Prize for me for building a time machine. Because I can cover more distance, because I can just add more momentums to light and create longer and longer diagonals. Yes, it'll cost some money, but it's a little money for time travel, right? I'm sure I should be able to get the government to go for this one. Surprised nobody else figured it out. It just seems like such an obvious thing to take advantage of. So I guess, and so Hythloday also thinks that when we see Venus in the sky, we're seeing it where it is now, not where it was. Everything we see in the sky, the sun, 8 minutes away, we're seeing it exactly where it is now. Because, well, the sun's a bad example because that's not the thing moving, is it? So yeah, you can't use the sun. You have to use one of those moving things, the moving bits. But yeah, the radiation coming off a planet moving in some other direction than we're moving, yeah, no worries. You don't have to account for just the Earth's movement. So anyway, this all, he ragged on me because, I got the full story wrong. And it was, Newton did, I did say in the video, I made every indication this was not a history I had studied, that I had precise knowledge of. I said right in the video, I don't know if Newton knew the speed of light. Yes, he did. And so Newton already had fixed the equations. He had already fixed the bad observations that were given to Kepler, I think, right? I mean, there was some rich guy who had some sort of island, and he was the one that did all these tons of observations of all the celestial bodies, and it was that data that Kepler and then Newton were using, because they didn't make all the observations themselves, and that data had to be fixed, and when they found out the speed of light, they fixed it. It still had other problems, but they got fixed a bunch of it. But anyway, okay, so, alright, maybe that's not accurate. I think that's fairly a close approximation to how things went. But whatever, let's just say it's not. And let's just pretend that this notion that where you're seeing something position-wise doesn't have anything to do with how long it takes light to get to you, and the fact that the light's coming in a straight line to you, and that it's not moving with the object. So I have to think of some other more real experiments that'll demonstrate this, but I mean, real world stuff. I think, okay, here's an example. But I don't know if you can find this detail somewhere. Alright, when they shoot a laser, there's a little reflector on the moon, and they have to shoot a laser at it. I'm sure they compensate for the fact that where they see the moon, I mean, they look for it in the telescope before they shoot the laser. So they look for it, they aim at it. And I'm sure they compensate for that 2-second difference in what they're seeing the position as being and what the actual position of the moon is. And they actually compensate for the 2-second difference that will be a result of the movement of the moon. So they aim in a different location. They don't aim where they're seeing. But anyway. It's preposterously irritating. Anyway, but anyway, yeah, it is interesting. I'm just saying that I don't know why all this talk about this problem with the speed of light. I mean, all you have to do is give a light source a perpendicular movement, and you automatically have moved light faster than the speed of light in terms of communicating. You've had light go somewhere, a longer distance. Yeah, it's jumped into the future. Jumps there. No way to get around that, really. I mean, there's just no way to get around this. This line is longer. It just is. And there's no way to get around it. Okay, so until next time. Yeah, I guess I'll have to go fiddle around, find crap on this one, but I just thought everybody knew this. I didn't think this was, I didn't think anybody would argue that we don't see things where they are, we see them where they were. The light hasn't moved to their new location with them. And that's the implications of this. So when you're looking at some cosmic object, you're really seeing it where it is, because the light kept its velocity. And no problem. It readjusted for you, so it's everything you see is exactly where it is now. Right now, that's where it is, because the light moved with it, like a baseball. Do you throw a baseball off a train and going 70 miles an hour, and if you throw it at the person, you're never going to hit them. You got to throw it behind them, because it's going to go 70 miles an hour towards them. Yeah, light doesn't do that.